Welcome back, my friends. Here we are again. We're going to talk some string theory today. We haven't done that for a while, so I'll tell you my thoughts on it throughout the video. Before we get into it, you should come download the free alpha for CalVPN, something I've created myself. And again, thanks to everyone who has already downloaded and signed up. It means a lot to me personally, honestly, it really does. And just again, one final thing, it's a brand new kind of, this is the future of VPNs. And you can bet that all big VPNs will eventually, just copy what I'm doing if they can manage to figure it out. Because it's going to be absolutely necessary in the future within the next 5 years. Also, if you guys are feeling generous, I've just created a LinkedIn page for CalVPN. So if you could come follow it, that would be awesome just to get some numbers there. So I'll put a link in the description to make it easy for you. Be much appreciated. The dog's back and he wants to say hello. How are we? He literally just stands here. What are you doing, creeper? Where are you going? You off? You don't want to be in today's video.
What is the true nature of the universe? To answer this question, humans come up with stories to describe the world. We test our stories and learn what to keep and what to throw away. But the more we learn, the more complicated and weird our stories become. Some of them so much so that it's really hard to know what they're actually about. Like string theory, a famous, controversial and often misunderstood story about the nature of everything. Why did we come up with it, and is it correct or just an idea we should chuck out? To understand the true nature of reality, we looked at things up close and were amazed. Wondrous landscapes in the dust, zoos of bizarre creatures, complex protein robots, all of them made from structures of molecules made up of countless, even smaller things, atoms. We thought they were the final layer of reality until we smashed them together really hard and discovered things that can't be divided anymore, elementary particles. But now we had a problem. They're so small that we could no longer look at them. Think about it. What is seeing? To see something, we need light, an electromagnetic wave. This wave hits the surface of the thing and gets reflected back from it into your eye. The wave carries information from the object that your brain uses to create an image. So you can't see something without somehow interacting with it. Seeing is touching, an active process, not a passive one. This is not a problem with most things. But particles are very, very, very small. So small that the electromagnetic waves we use to see are too big to touch them. Visible light just passes over them. We can try to solve this by creating electromagnetic waves with more and much smaller wavelengths. But in quantum physics, shorter wavelengths means more energy. So when we touch a particle with a wave that has a lot of energy, it gets a kick. By looking at a particle, we change it. In quantum physics, we cannot know where a particle is and where it's going with absolute precision. This fact is so important that it has a name: the Heisenberg uncertainty principle, the basis of all quantum physics.
So I've got a thought experiment for you. So imagine you have a magnifying glass, right? And you're going to look at a little region of space and time. And you just want to see what's there. Basic experiment. And look at the vacuum, what's there? And so what we learned because of quantum mechanics is to probe shorter and shorter distances because of Heisenberg's uncertainty principle. You need higher and higher energies. And that's why we have to build these huge, experiments, Large Hadron Collider, to probe, the smallest distances humans have ever probed. And that's kind of ironic, right? The biggest experiment in human history to probe the smallest distances. Again, that's exactly why, you need higher energies to probe smaller and shorter distances. And, without gravity, it would be no problem. So if you imagine a world with no gravity, too easy. You could probe arbitrarily small distances. You just ask the governments for more money for bigger, particle colliders, and you can probe smaller distances. But now let's put gravity into this world, and something bad's going to happen, right? At some point, you put too much energy into this small little region of space. I'm sure you guys know what's going to happen, right? What happens? Well, you collapse that region into a black hole. And, at that point, light can't escape, right? So just by trying to see what's going on in this little region actually makes a black hole. That makes it impossible to see what's going on. And this is first going to happen at about 10 to the minus 33 centimeters. Time on the order of 10 to the minus 43 seconds. And this is the Planck time. And these are absurdly small, like tiny. So just to give you an example, like perspective, the distances probed at the Large Hadron Collider, 1,000 times smaller than the nucleus of an atom, 10 to the minus 17 centimeters, which is 16 orders of magnitude in difference to what we're talking about. Just shows how ludicrous it is. But this simple thought experiment really demonstrates that there's no pointing, you can't give operational meaning to these small times and distances. And every time this happens in physics, where there's like this idea that you can't even give operational meaning to, it kind of, suggests that this thing is approximate and that it's not really there, that it actually emerges from something more fundamental. And in this case, it's kind of pretty crazy because it's, the notion, the actual, idea of space-time itself that needs to emerge from something more fundamental. So you might ask, if you know your stuff, if at those really small distances and times, right, like, does that mean space and time become like quantized? Just like electromagnetic radiation has a photon and everything, is in these little discrete bits. Well, I would tell you that's actually probably the most naive idea for what's happening. And, there's approaches. This is, to quantum gravity, which take this very serious, this idea, right? But lots of people don't. They kind of think it's just naive, right? And this is because, the fact that everything's broken into little bits is kind of in conflict with, special relativity, because you're saying, in some reference frame, you can't talk about time separations that are smaller than a tiny certain amount. But Einstein tells you there's another frame of reference moving relative to that one at a very high speed where those, separations in time become a lot larger. And, there's lots of arguments that can be made for the spatial separation. So it's difficult to lay down some, ladder structure on space-time, in a way that's compatible with relativity. And so it's not that there's, some atom, like small bits of space and time, but there must be something more interesting and subtle going on, right? And you might have heard of something called holography, which gives, a more radical picture for how this, separation, this discreteness might happen. And, it's like if you try to describe what's going on in this, small area of space and time, again, you might think that there could be these little blocks, like in Minecraft, building the universe, building space-time. And maybe they're like the Planck length, in size. But that would lead you to think that, any volume of space, that is somehow, that the volume divided by this unit of Planck volume of number of bits of information that you need to like specify in order to see what's going on. On the other hand, holography is this idea that there's a significantly, smaller number of bits of information you need to specify that isn't restricted to the volume of space, but instead, restricted to the boundary of space, right? Which is, the surface. And so that the number of bits that you need to specify is like the area of the surface in Planck units, right? And that might sound counterintuitive, and that's kind of for the reason hologram, right? Because it's roughly the way in which three-dimensional information is decoded in a two-dimensional hologram. We know that a 2D hologram encodes three-dimensional information in like pretty subtle ways, right? And just like that, what's going on inside space-time is encoded in very subtle ways in terms of what's going on at the boundary. And this is a qualitative idea that's been made, brought into focus in string theory in the last decade or two now. And it gives it a good example of that notion of emergent space, at least, right? From that idea space-time's got to come from something, right? It's got to emerge from something. But in certain kinds of space-time, which are like 10-dimensional, string theory does all this crazy stuff. But, we understand that there's this completely equivalent description of what's going on in this space-time that lives on the boundary of space-time in terms of a 4-dimensional ordinary theory of particles. And not very different from the standard model of particle physics. No gravity, no extra dimensions, 4 dimensions. It's obviously different in detail to the standard model, but it's the same kind of theory, known as a quantum field theory. ordinary theory without gravity. This ordinary theory describes everything, that goes on in the bulk of this space, which has 10 dimensions, strings, gravity, everything else. One of the cool things we've learned about string theory in the last decade is that it's actually not a theory of strings. There's actually something deeper and crazier going on than just points being replaced by, these strings. and it's this idea of holography is one of them, right? And like we talked about it before, which is a pretty concrete example. And there's more examples that give emergent space. There's a problem though. We don't know how to extend those ideas to include time, right? And clearly, we need to understand time if we want to understand these questions about cosmology, the multiverse, accelerating universe, anything to do with time and cosmology. We have no idea what's going on right now. We're in confusion. We don't know how to generalize those ideas to time. Without understanding emergent space-time, we don't really understand how to address any of the really fundamental questions that, quantum mechanics and relativity were meant to address, like what happens at the center of a black hole, what the origin of the universe means. And so, like emergent time is just like, it's pretty clear intellectual bottleneck, right? Emergent space kind of seems like child play nowadays in comparison, but it's just this time stuff, right? It seems like the key stumbling block. It seems like it could hold a lot of the mysteries of cosmology.
So what does a particle look like then? What is its nature? We don't know. If we look really hard, we can see a blurry sphere of influence, but not the particles themselves. We just know they exist. But if that's the case, how can we do any science with them? We did what humans do and invented a new story, a mathematical fiction. The story of the point particle. We decided that we would pretend that a particle is a point in space. Any electron is a point with a certain electric charge and a certain mass, all indistinguishable from each other. This way, physicists...
All right, all this bit is pretty good, all right? This is actually pretty good stuff because this isn't explained very well in most places, and I like this. So yeah, rewind that a few times.
...could define them and calculate all of their interactions. This can be made precise in quantum field theory, and this...
When he says a point, you might be like, what do you mean a point? Like, he literally means an infinitesimal point that has no size.
...solved a lot of problems. All of the standard model of particle physics is built on it, and it predicts lots of things very well. Some quantum properties of the electron...
But it doesn't, it predicts even more really badly. So yeah, it's pretty amazing, absolutely amazing what it can predict, no doubt about that. But let's not get ahead of ourselves, right? There is so much it is terrible at predicting. Anyway.
For example, have been tested and are accurate up to 0.0000000000002%. So while particles are not really points, by treating them as if they were, we get
he just said whilst they're not really points, that we don't know that. They really could be point-like, these infinitesimally small points.
Pretty good picture of the universe. Not only did this idea advance science, it also led to a lot of real-world technology we use every day.
World, man.
But there's a huge problem: gravity. In quantum mechanics, all physical forces are carried by certain particles. But according to Einstein's general relativity, gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage. To put it simply, gravity is a theory of geometry, the geometry of space-time itself, of distances which we need to describe with absolute precision. But since there is no way to precisely measure things in the quantum world, our story of gravity doesn't work with our story of quantum physics. When physicists tried to add gravity to the story by inventing a new particle, their mathematics broke down. This is a big problem. If we could marry gravity to quantum physics and the standard model, we would have the theory of everything. So very smart people came up with a new story. They asked, what is more complex than a point? A line or a string? String theory was born.
All right, that's not how it went down at all. And why are those people looking so old and like about to croak it? Just like literally leaning over. Okay, to give you a deeper idea of where it came from, right? This guy had this mathematical formula for for something called a scattering amplitude. We're not going to talk about that. He had this formula, it was a function of the momentum of the incoming particles and the outgoing particles. And it's this famous formula called the Veneziano amplitude, right? But it was just this mathematical formula. It had these two gamma functions in the numerator and one gamma function in the denominator, right? And it basically had a lot of interesting mathematical properties, very interesting. And this guy, and no one realized, they didn't know what the underlying physics of it was, right? It was just a mathematical formula to them. It was this guy called Nimble and Susskind who realized that it was describing the scattering of strings. Up until that point, that word string, it didn't appear anywhere in physics. And if it did, it probably had something to do with, mathematical study of violin strings. It turns out that quantum chromodynamics, it basically, describes strings. It was like this mathematical field theory, which was describing like these string-like excitations, right? And so that idea of strings for hadrons, for strongly interacting particles, basically, came from quantum chromodynamics ideas. So it comes together, and it turned out to be the same, right? So we now know that protons, neutrons, mesons are really, string-like excitations. Anyway.
What makes string theory so elegant is that it describes many different elementary particles as different modes of vibration of the string. Just like a violin string vibrating differently can give you a lot of different notes, a string can give you different particles. Most importantly, this includes gravity. String theory promised to unify all fundamental forces of the universe. This caused enormous excitement and hype. String theory quickly graduated to a possible theory of everything. Unfortunately, string theory comes with a lot of strings attached. Much of the maths involving a consistent string theory does not work in our universe with its 3 spatial and 1 temporal dimensions. String theory requires 10 dimensions to work out. So string theorists did calculations in model universes, and then tried to get rid of the 6 additional dimensions and describe our own universe. But so far, nobody has succeeded, and no prediction of string theory has been proven in an experiment.
One of the ways that we've hoped, string theory, we haven't achieved this yet. We've achieved it might make contact with experimental physics, is to see like a signature of extra dimensions at places like the Large Hadron Collider. Hasn't happened yet. Doesn't mean it won't happen. But that would be, a pretty awesome moment in the history of our species if, we could get data in our dimensions, gave us sort of like, evidence that, our dimensions are not the only dimensions. That would be pretty mind-blowing. Another experiment we imagined might give us, some evidence. It was a long shot though, but we thought when you slam protons together at very high speeds, if there are these extra dimensions and if they have the right form, and that's a hypothesis, might not be correct, right? But when this happens, it creates this debris, right? And it might be able to leave our dimension and insert themselves into other dimensions. And the way we figured we could potentially recognize this, is that there'd be more energy before the collision than after the collision, because some of that energy was taken away from the place that our detectors could detect it. And I guess that could be some bit of a concrete way to detect it. Another way we could do it is like with gravitational waves, because gravitational waves exist within it's associated with the shape of space. Gravitational waves in principle could provide a way of like scanning, CAT scanning the extra dimensions if you had really good control over those processes, but we don't yet. So I'm sure we will one day if we don't destroy ourselves.
So string theory did not reveal the nature of our universe. One could argue that in this case, string theory really isn't useful at all. Science is all about experiments and predictions. If we can't do those, why should we bother with strings? It really is all about how we use it. Physics is based on maths. 2 + 2 makes 4. This is true no matter how you feel about it. and the maths in string theory does work out. That's why string theory is still useful. Imagine that you want to build a
So string theory is actually more useful than he just explained. There's been actually a lot of breakthroughs in mathematics that have come from string theory and people working in string theory. So it is actually arguably useful. If it provides new insights into math, which is maybe the language of the universe, I would argue it's actually beneficial to keep just digging further. And even if it didn't do that, I would still argue it's very beneficial to dig further. And we should have people working on this stuff because it does conveniently solve a lot. And, just because we can't come up with any experiments right now because the energies involved don't make a lot of sense, well, let's just put it on the shelf and hopefully one day we can.
But you only have blueprints for a small rowing boat. There are plenty of differences: the engine, the materials, the scale. But both things are fundamentally the same, things that float. So by studying the rowing boat blueprints, you might still learn something about how to build a cruise ship eventually. With string theory, we can try to answer some questions about quantum gravity that have been puzzling physicists for decades, such as how black holes work or the information paradox. String theory may point us in the right direction. When used in this spirit, string theory becomes a precious tool for theoretical physicists and help them discover new aspects of the quantum world and some beautiful mathematics. So maybe the story of string theory is not the theory of everything. But just like the story of the point particle, it may be an extremely useful story. We don't yet know what the true nature of reality is, but we'll keep coming up with stories to try and find out until one day, hopefully, we do know.
Something really important to understand is that often the concepts that end up being relevant, that we end up needing to understand things more deeply, so foreign to the ideas that we currently have that we really can't even begin to articulate the question before we, are even within the vicinity of the answer. And I think that's a really interesting way, this part of science works. Because it's so different to the cookie cutter description that someone makes a hypothesis, experimentalist goes and checks if they're right. No, you're not right. You're right. Go back and make another hypothesis. I think it's a bit of a outdated view of how science is done. It's not really close to the truth, particularly in theoretical physics, and particularly in this area, the areas that involve these big, deep conceptual questions. We don't even, as we said, we don't even know if we're asking the right questions until you're in the vicinity of the right answer, so you have the whole car before the horse situation. And, often we have the correct equations for a long time before we even know what they mean, right? And so nothing works in that straightforward cookie cutter way. But what that means, right, is that we have to be pretty cautious of what we mean by words. We have to be precise. And so, for example, the electron, when we say electron, we mean something very specific. And it's actually really different to what we mean, not quite the same, by what we meant by an electron 100 years ago because of quantum mechanics and stuff, right? It won't be very useful to you, but what we mean when we say electron right now is an irreducible representation of the Planck array group spin half, right? And that's it might not mean anything to you, it might, but that's not what J.J. Thomson, who discovered the electron, would have described it. Oh, he's a good boy. He's a good boy.
This video was
excellent friggin' video. That was so beautiful. We'll leave it there. Make sure you go check out CalVPN, download the free alpha, come help me out, and I'll catch you guys in the next one. Let me know what you want me to watch next.